This video we're going to talk about L'Hopital's rule. Now, L'Hopital's rule comes up when we start dealing with indeterminate forms, which we talked about in the first of Calculus 1. This rule, you're going to wish you knew this rule back in Cal 1. It would have made your life a little bit easier in evaluating limits. All right, so what does L'Hopital's rule say? It says, suppose that f and g are differentiable where the derivative of g is not equal to 0, okay, on some interval that contains some a value with the possible exception of a itself. So that's that typical limit idea. You've got some interval and a is in that interval, and maybe it's differentiable everywhere in this interval in some neighborhood around a with the possible exception of a itself. That's that typical limit definition phrasing going on there. So what does L'Hopital say? If the limit as x goes to a, so as we approach a from the left and the right, of the fraction f of x divided by g of x, this is why we don't want g equal to 0, then, okay, hold on. So if this is an indeterminate form of the type 0 over 0, and this could be plus or minus 0 over 0, or infinity over infinity, okay? So if you're in indeterminate form of this type or this type, then we can use L'Hopital's rule. Then, what does L'Hopital's rule say? It says the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x, so we take the derivative of the numerator, divided by g prime of x, the derivative of the denominator, okay? So this equals here, what I like to do to designate that I use L'Hopital's rule is I put a little L with a circle over the equal sign, and that tells me that you use L'Hopital's rule to get from this step to this step. Take the derivative of the numerator, take the derivative of the denominator, write it out. If the original limit here was indeterminate form, then that's what allows us to do this here. Okay, now notice how we're limiting to a number. So it's like we're taking the limit as like x approaches 2, right? What if instead we were taking the limit as like x approaches infinity? Would it still work? So turns out that plus or minus infinity still works with L'Hopital's rule. So you can still do this. You just take the derivative of numerator, take the derivative of denominator. As long as your indeterminate form is one of those two types there, you're okay. Okay? So indeterminate form means that when you evaluate the limit, we cannot determine the answer without further explanation. Okay? So when you plug it in, you must have 0 over 0 or infinity over infinity, okay? So you got to have one of those in order to use L'Hopital's. All right? So let's do a problem where we use L'Hopital's. So here's an example. Limit as x goes to 2 of x squared minus x minus 2 over x squared minus 4. Okay, first thing I always do whenever I see a limit problem is I just plug in, see what happens whenever I plug in. So whenever I plug in, what do I get? I get 2 squared minus 2 over 2 squared minus 4. So this is going to be 4 minus 2 over 4 minus 4. That's 0 over 0. So I write out form. What is the form? It's 0 divided by 0. So I know because it's 0 divided by 0, it's an indeterminate form, Therefore, I can use L'Hopital's rule. It says take the derivative of the numerator, take the derivative of the denominator, and then evaluate the limit. So that means by L'Hopital's rule that this is equal to, see how I put the L with the circle around the equal sign above it? So this is x goes to 2 of, well, what's the derivative of x squared? That's 2x. What's the derivative of negative x? That's negative 1. What's the derivative of negative 2? That's 0, right? So in the denominator, derivative of x squared is 2x. Derivative of negative 4 is 0. So now, what do I have? Well, let's plug it in. That's 2 times 2 minus 1 over 2 times 2. So that's 4 minus 1 over 4, so that's 3/4. So my answer is 3/4, okay? Now, if you think back to Calculus 1, the old way of doing this problem, what you would have done in the past is you would have said, okay, this one and this one, looks like I might can factor them. It actually factors to what? X minus 2 times x plus 1. Okay, and then in the denominator, that's a difference of squares, so that's x minus 2, x plus 2. And so what do we know? This factor and that factor cancel, and so I get limit as x goes to 2 of x plus 1 over x plus 2. When I plug that in, 2 plus 1 over 2 plus 2, then that still gets me my 3/4 there. So that's the old way of doing things. Now we're going to use the L'Hopital way, and I think you'll find that it's faster and better. Okay. So let's do one more, just to nail this home. How L'Hopital's rule is actually better, because if we do this problem here, limit as x goes to infinity. Well, what do we get? Ln of infinity, well, what happens to a natural log as x approaches infinity? As x goes to infinity, what happens? This actually, ln x goes to infinity. It goes ever so slowly to infinity, but it is going to infinity, all right? And then what about x plus 1? That's a line with slope 1. That's going up to positive infinity too. So that means that this is of the form positive infinity over positive infinity. So it's indeterminate. If you were in Calculus 1, you would have to stop right here. There's no way to do this because we don't have any way to factor ln x and x plus 1 to see where anything cancels like we could here, right? So only thing we can do is use L'Hopital's rule. So what does L'Hopital's rule say? So limit as x goes to infinity, ln x over x plus 1. So I'm going to use L'Hopital's, and whenever I do this, I have x going to infinity. What's the derivative of ln x? That's 1 over x. What's the derivative of x plus 1? That's just 1. So what does this equal? This is equal to limit as x goes to infinity of 1 over x. Divided by 1 is just 1 over x. And now as x gets really big, but 1 stays the same, constant, what's going to happen? Well, this is going to pull me down to 0. 1 over something really big is basically 0. Okay? So what is this telling me? In a way, what this is telling me is that when I'm comparing two functions here, and the denominator is infinity and the numerator is infinity, but this whole ratio goes to 0, that means the bottom is going to infinity a lot faster than the top is. So that means that x plus 1 is a dominant term compared to ln x. And you can see that by the graph here. This is x plus 1 is going to infinity quicker than the ln x is, okay? So we've mathematically proven different growth rates here. And so what I want to finish this video on is just an emphasis on growth rates that we're going to assume from this point. You're not going to have to prove this. This isn't a proof-based class, but we're going to assume these to be facts going forward through this course. So it's very important that you understand this. So the growth rates of functions. Okay? We're going to talk about this more in detail when we get to sequences and series, with a big part of this class. I call this the race to infinity. Race to infinity. Right? So as x approaches infinity, which one's growing the fastest? Well, we'll start with the slowest one. The slowest is the natural log of x. So that's the natural log. So anything logarithmic. Okay, so nothing special about base e. It could be log x, log base 2x, whatever, right? Just anything logarithmic. That's the slowest growing. The next in the list is polynomial. So x to the n is polynomial. Not poly, polo. Polynomial. Okay. Could be radical. You could have like x to the 3/2, something like that. X to the 1/2. Remember, that's the same as the square root of x. Polynomials, rational or integer exponents there. Okay. Then next up, we would have exponential. So like a to the x. So instead of the variable being the base, now the variable is in the exponent. So this is the exponential. Now, exponential is a growth function only if a is greater than 1. Okay, if it's less than 1, it's a decay function. Next up, one that you may or may not be familiar with. This is found in statistics. It's the factorial. So factorial growth is faster than exponential. So how does factorial work? If I had 5 factorial, this would be equal to 5 times 4 times 3 times 2 times 1. The physical interpretation of factorial, what's it useful for? It tells you how many ways you can rearrange a set number of objects. So if I have 5 different objects, say I've got like A, B, C, D, E. 1, 2, 3, 4, 5. There's 5 things. That's one ordering of those 5 objects. Another ordering could be like A, B, C, E, D, right? So the question might be, well, how many orderings are there of those 5 objects? Well, there are 5 factorial orderings. 5 times 4 times 3 times 2 times 1 is 120. You see how this grows really fast, really quickly, okay? So just for example, like if you put 10 factorial in, that's going to give you a monster number. Okay, so 10 factorial, let's see. Hold on a second. 10 factorial, that's 3,628,800. Okay, so that's over 3 million. Okay, so it's growing really quickly. So it's even faster than exponential. Now the fastest one we're going to run into in this course is x to the x. This, my friends, is called the super exponential. The super exponential. Not only is the base variable, but also the exponent is variable. And so it's growing super exponential. So like 5 raised to the 5 would be like 5 times 5 times 5 times 5 times 5. You see how that's better than 5 factorial because the factorials decrease. Each factor gets 1 less than the other. With the super exponential, it stays in it. It's that number multiplied by itself that many times. Okay? So pretty fast moving function there. Now, why might you need a super fast moving function? Well, maybe you're trying to model something in some equation that, maybe it's modeling some type of meteor falling from the sky, or maybe you're trying to create an algorithm that computes monstrously large numbers that can be coded and used as a cipher for digital encryption. So there's several applications that can make you a ton of money in programming and doing all sorts of decoding and encryption ciphers with large super numbers. So that would be a field that you would use super exponentials in. Okay, guys, so that ends this introduction to the L'Hopital's rule, and we're going to jump into more examples in the next video.